final project with the topic body simulation with three methods. And first, this is my outline. I will introduce the three methods and then talk about how I construct the tree code with Python and share my results. And next, I will talk about some possible improvement of my own Python code. And finally, I will have a quick summary. First, what is the tree method? The main idea of the tree method is use the cells instead of particles. Like this structure, this is the cell and this is a particle. And when we sum over the force to the particles, instead of sum the force between particles and particle, we will now use the cell and we will now use the cell instead of one particle. So when we add the acceleration of one particle, we will sum over the force between the cell unit to and the particle. And this is how to determine which cells are needed. So the condition is that if the length of the cell divided by the position difference between the cell and the particle is less than some value theta, and you add the gravity between the cell and the particle, and if it is not satisfied, and the function will run for all subcells and do the same thing until all subcells are considered. And next problem is how to cut the cell. And if the particles inside a cell is more than one, and we will now cut the cell into F subcells. And for my own code, each cell will record the ID of particles which is inside the cell. So as the function cuts the cell into S subcells, these IDs will move into the subcells. And next, the ID from the original cell will be deleted, so that each particle will only inside one subcell. And next is the structure of my code. And the main code is the executive file, which will be executed by the terminal or the script. And next is the classes and constant file. The classes file will define the class of the tree and particles, and the constant file will have some useful constant such as the AU in the units of centimeter. And the initial file, tree structure, search tree, evolve, visualize, energy, and IO file are used for solving some problem in certain steps. Next is the data structure for my own code. And there are two types of data. First is particle and the second is cell. And for the particle class, it has the data of mass and position and velocity, which is very simple. And for the cell class, it has the data of the cell mass, which is sum over all particles inside the cell, and will not remove if the particles are moved into the subcells. And also, it will record the position of the cell as well as the weighted average position of the cell. While we need to position in this data. In this section, first the position is used for some slice plots. If we use the position of the cell, we can easy to know the boundary of the cell is at what position. And for the first calculation, we will use the weighted average position, so the error of the code will become less. And also it contains the length of the cell, and as previous slide, it will have the particle ID inside the subcell and the subcell inside the cell. And like this figure, the biggest structure, I will call it as the tree, and the tree has the attribute subcells, and the subcells data will have 8 subcells. So each subcell will have it is also the cell class. And if the subcells are also cut into 8 subcells, and the cell will have the data subcell for each new subcell. And this is how we determine the initial condition. And there are 2 ways. First is obtain the possibility distribution for each coordinate. And if you use the spherical coordinates, you will need the r, theta, and phi, and you can generate random number following this possibility distribution and transform them into the Cartesian coordinates. Or also you can directly use the possibility distribution in Cartesian coordinates if you are able to know about that. Or the second way is simpler. If the initial condition is homogeneous for some region and the other region doesn't have any particle, and you can generate random xy at z. And if the particle is not in the region you want, like this x, and you can roll it again and until it is inside the region you want, and you can do it again and again until the total number is satisfied. And what will the code do in each step? First, the tree structure will be constructed, and it will evolve the particles with the tree structure construct in previous step. In previous line, and with the archival method. And for certain step, the code will output the slice plot and write the data in a text file, which will show in next slide. And the fourth is possible, and I don't have it in my own code, but it is hard to modify. And for some certain step, as the previous line, the code can output the particle data as a NumPy array. And if you want to continue the simulation at some step, you can just read the NumPy array as the initial condition and the time, and you can just continue the simulation from that step. And there are 2 output file types in my simulation. First is the slice plot, and this is the tree structure at the for the initial condition, and and there are the weight average position for the cell in this plane, and also a lot of particles in this slice plot. And the right hand side is the data, which is in the text file. I call it as data.txt. And the first line is the type of each value, and it contains the energy and also kinetic potential energy. Also, it contains the direction, angular momentum, and the time. And for this data in the text file, it will be easy to read by some Python code and have some diagram of the energy evolution or angular momentum evolution. So this is my first result with the condition spherical collapse, and it is not physical at all, and will have extreme value as the particle fall into the center, but it is quite fun. And the simulation setup is 1000 particles randomly generated in the sphere with the radius 500 centimeter, and each particle has a mass 10 to the 10 gram, and evolve with the t for 0.1 s. Actually, the speed of the collapse will determined by the mass times the dt. So I choose the small dt since I have choose a large mass in previous line, and I will output the result for each second, which is 10 steps. And this is the energy evolution and the angular momentum evolution. The potential energy is always negative, and the kinetic energy is 0 at the beginning since all particles are stable, and the total energy is the kinetic energy plus the potential energy. So in this case, the total energy is always negative, and the angular momentum is very unstable. It is sometimes positive and sometimes negative, but because this condition is unphysical after the particles are falling to the center of the system, so it is not important in this case. And you can see that the total energy does decrease in this region, and this is because the distance difference between the particle and the cells will add with an artificial value, which is 10 to the minus 2 in this case. So the kinetic energy will not explode in this case, but the total energy will become less. And the right hand side is the simulation with the artificial factor 10 to the minus 1. So it collapses, and many of them are still at the simulation region since the force is not very strong. And the right hand side is the case with the artificial value 10 to the minus 2, so the force will be bigger for this case, and many particles will run away from the simulation region. And also, since the numerical error, the center of mass is not stable, so it will go from the center to other position, and this particle will stay at the center region since the artificial value is smaller. And next simulation will be more physical, and this is the solar system with a lot of asteroids, and the simulation setup is 992 asteroids in the region between Mars and Jupiter, and each asteroid has the total mass of the real asteroid between Mars and Jupiter divided by the number of asteroids and times the random factor from 0.5 to 1.5. And the less edge particles are the edge planets, and they are set on the same plane, and the asteroid has the random theta value, and the phi value are from phi value are from negative 20 degree to positive 20 degree, and thus the sun is treated as a tiny independent potential, so we will not consider the sun as a particle, and the sun will still give the force and the potential energy for this simulation. And the energy evolution is very flat, and all of the energy only have very little error in this simulation. It is very stable for this case, but since we treat the sun as the external force source and potential energy source, so if we consider the sun as a particle, it may not be very stable at all, but it is but the error for this is still very small, so the tree method does not give much error for this simulation. And the left hand side is the XY plane slice plot for the simulation, and you can see the planet is orbit around the sun, and here is an interesting part, and here is a planet, but after some steps it fall into the region with the value less than 0, so it's not inside this cell, so this cell will become empty, and it can be discovered in next slice plot. And this is the Wiley slice plot, and here is the particle at this place, and it go into the lower cell at this step, so it will disappear from this slice plot. It's very interesting, and there is some possible improvement for this tree code. First is try with more particle. For the time limit, I only test for 1,000 particle, and it can add some MPI parts to shorten the time for simulation, and it can transform into Julia or C++ to become more efficient, and the time can be adapted to prevent some extreme acceleration, and it can also compare with the direct unbodied simulation result, which is right for like GPU. And this is my summary. And first, my tree code can simulate with some physical condition with a little error, and some error will probably generated by the small r value to prevent extreme value, which is talked in previous session. And the Python is easy to add a lot of function for the simulation, and it is very convenient, but it takes a lot of time to simulate. So it's better to try with the C++ or Julia. And MPI function I have tested for some time, and it is success, but it takes a lot of time. I think it takes that time to transfer data. And for my code, it will have complicated tree structure, so I think the MPI will take a lot of time to transfer the tree structure to other core, and it might become more efficient if the N is larger, and the time to calculate the force will become longer than the time to transfer data from the rank 0 core to other rank core, but the time scale will be too long for Python, so the better way is still transform the code to C++ or Julia. And this is my reference.